And hello everybody, welcome back. We're gonna continue our discussion with OpenFoam CHT multi-region foam case. Okay, so last time we were talking about filling out the thermophysical properties for the oil and sphere region in the constant directory. So we are talking about giving it proper thermophysical properties, and we have discussed thoroughly how that was done. And the sources are given in the last video or last few videos, where we dealt with the conductivity of oil along with other physical properties, as well as the density as well. And now it looks like there is nothing much more we need to do in this constant directory. So we have all the properties we need for the sphere and the oil regions in our simulation. And also we have pretty much done what we need to do with the zero region, because that was dealt with in the change dictionary, right? So, and we know what rho stands for. Rho just stands for the density density, but it will be changed according to what it is set in the constant directory, so no need to worry about that. Next thing we need to deal with is whatever is inside the system directory. Alright, so again in the system directory we have two files, decompose parallel dictionary and decompose parallel dictionary 6. These are for parallel processing. Now we're not going to talk about that just yet. We're going to talk about the series one because we want to do it simply first. So block mesh dict, control dict. These ones you should know. I'm not going to discuss them again. Mesh quality dict, snappy hex mesh dict, and surface feature extract dict. These are meshing tools with respect to snappy hex mesh in particular. So they deal with that. Now, to see what files we need in here and here, we'll need to check what is inside the original files. Meaning to say, okay, for our oil and sphere regions, there needs to be fvSchemes and fvSolution and some other kind of files in there as well. Okay, and obviously there's a fvSchemes and fvSolution here, but as we discussed before in few videos before, there's basically no information here whatsoever, so we don't need to worry about filling these things in. We'll just leave it there as it is. But let's go for the oil one first. So there are three files here: change dictionary, fvSchemes, and fvSolution. Now as we might have guessed, fvSchemes is also empty here. So to check what we need, we can go to bottom air to kind of borrow whatever they have from the fvSchemes there. And even one more interesting note, there's a decomposed parallel dictionary here as well. And this is something we might want to take a look into later, especially when it comes to doing a parallel simulation for chtMultiRegionFoam foam, and that indeed will be pretty useful. So let's look at fvSchemes first inside the bottom air directory. So DDT schemes, default is Euler. So this is finite volume schemes. So this tells you how you're supposed to do all these schemes. I mean, how the solver is going to solve. So it's always going to be these parameters here. Again, yeah, these are all Gaussian schemes. So the simple way, of course, is to just copy and paste this entire this entire folder. Copy every single entry here and just paste. I mean, that's what we can do for templating. If nothing goes wrong, then we can assume that this is the correct way to do it. Okay, so for starters, we'll do this first. Of course, it's always useful to understand this, but understand what these schemes are talking about, but I'm not going through that in this video. Okay, so let's do an undo. I think I put an insert and paste. DDT schemes, gradient schemes, divergence schemes, blah 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 blah. And of course, we can save this, and oops. Okay. Insert, paste, save and quit, or save. And just for reference, if you've seen the snappy pipe tutorial, you can also see the FV schemes here to see what's the comparison. So DDT schemes is again Euler, because there's a bit of a spacing here. So this is something we are familiar with, as in at least it's a case we are familiar with, right? So I can do an Euler scheme, and it's a Gauss linear gradient scheme, because there seems to be a gradient of P as well. So that seems to be missing here, but no matter. You can take a look at the divergence schemes. Default is none. UKH. These are things that are found here, and this one is rho nu effective def 2 t gradient of u. This is a Gauss linear. I'm going to go through that now. Laplacian schemes. Default is Gauss linear corrected. This one is Gauss linear orthogonal. Okay, so it's slightly different. Okay, interpolation is a linear. SN gradient schemes are corrected. Maybe I should, yeah. I'm not going to go through too much in detail what these are. I mean, it's worked for the previous solution, so you just assume that it will work. You can talk about customizing that next time. Yeah, or if I have time. But let's just copy all of this first. Okay, so the solvers are over here. Okay, for the fluids side. Again, all I'm going to do is going to copy and paste all of this. Okay, apparently I cannot copy everything at once. So okay, I'm gonna copy up to this pimple. Okay, copy, and VI, go a file back and go to oil, fvSolution. Okay, I'm gonna copy up here first. I'm gonna paste it here, insert and paste, save and quit, VI fvSolution, and then after the pimple, it goes all the way down. So this is the pimple entry, and relaxation factors are here. So okay, the solver is there. Okay, so solver is there. You can see the brackets are highlighted. This one closes with this, but we still need to put the pimple scheme in. So insert and paste. So the pimple scheme is there. Save it. And we notice that there's a momentum predictor, n correctors, and n non-orthogonal correctors there. So okay, so we have a number of correctors there. We have a momentum predictor, which is okay, a slightly different from the normal pimple foam thing we are used to. If you've seen my other tutorial on pimple foam, so this is what what the entry is like. Okay, so Again, we can actually change a little bit of the pimple algorithm here. So there is a momentum predictor, which is not an entry that's available here. This is in my thin pipe flow snappy xmesh kind of a file. But okay, so we can actually copy this entry over, paste it here, because we know this works from our last tutorials on PimpleFoam. So hopefully you have seen that before. Okay, otherwise you can take a look again. Alright, so next is we'll need to put this in, and the relaxation factors as well. Now of course we see that the relaxation factors here, they are set at 1 and not some fraction of 1, which is okay, sure. We'll need to add some things in as well. Okay, so yeah. So anyway, we might want to do some correction here with respect to this PimpleFoam. Yeah, we want to do some correction here to maybe satisfy what we are doing with this pimple setup. Okay, with residual controls and everything, based on what was discussed in the PimpleFoam videos. You can see my other playlist. Yeah, so again, if just a quick revision, you can take a look at this one. So we use a simple pimple and piezo foam. Okay, and correctors is used by piezo and pimple, and it's to set the number of times the algorithm solves the pressure equation and momentum corrector in each step. It's typically set to 2 or 3. This one's non-orthogonal, I think we've gone through before. Now this is end outer correctors, which normally we have that entry over here in PimpleFoam. Yeah, we should have that residual control here in PimpleFoam. Yeah, so by default it is set to 1. So if you don't see the entry over here, it is by default set to 1, and it replicates the piezo algorithm. So momentum predictor, yes, this is the entry that we haven't seen before. It's the switch that controls solving of the momentum predictor. It's typically set to off for some flows, including low Reynolds number and multi-phase. So okay. So yeah, on the predictor step, we know that this is the step that we use to solve the discretized moment. We get the pressure field by guessing the discretized momentum equation. So I think that's something we want to keep. It is basically, you know, I think we talked about outer loop before in the PimpleFoam videos. So that's always important to know. Okay, maybe I want to change something here. We want this to be controlled by residual control. So, and non-orthogonal correctors, maybe I'll just put it as 1, and correctors I'll put it as 1 as well. 1 and 1. Okay. And let's put an outer corrector, the entry there, as 1000, because I want this to be controlled by residuals, not by you know, finishing the thing, because I want to use pimple control, not what do you call that, piezo kind of a mode. So I have a residual control here, and looks like there is one more field I kind of need to take into account. So I'll put it here, residual control, with the specific tolerances there. And maybe we want to take a look at one more tolerance, which is, I think, pretty important. Okay, not rho, not PRGH. Okay, but maybe the H field, because H fields, the enthalpy field is not quite given here. So it looks like we will have to define it over here. We want the thing to be controlled by the tolerance. Okay. So anyway, just for interest sake, we can look at the solvers. In here is using a PCG solver, P and PRGH final. We use the solvers GAMG. Okay, so it's a slightly different model with a Gauss-Seidel smoother. Okay, and U, H, K, epsilon, and R, etc., etc. So this is a K epsilon model only. There are not other models here. The solver is PBICGS tab. It's a different one. This preconditioner, DILU, tolerance and relative tolerance as such. Okay. Likewise, the final one, we copy and paste everything from the U, and we just have these two little things added in. Now, of course, all these things are useful to know. We can tweak these things later on, maybe in future iterations, but now let's just focus on the residual control first. Okay, so let's do a H field tolerance control. So H. Now, of course, if something goes wrong, we'll know where to take a look. Yeah. So first thing, I want a tolerance. Okay, I'll just put a phi e minus 2 and rel tol. I'll just leave it as a 0. Okay, so this is the residual control. Okay, I want to do it by residuals. Yeah, so next thing, we take a look at the relaxation factors. We have, instead of H and U, we add 1. So H dot star, U dot star. So we don't just want that. Okay, we want something different, which is not 1. Maybe a relaxation factor of 0.4, just to kind of control the thing. So yeah, let's take a look. Maybe we can start changing some things here, such as putting the field what do you call that? Field entry in. Okay, I'm just gonna copy this and paste. Hopefully there's no harm done. If there's harm done, then we'll go through the debugging, and then we can use that opportunity to learn a lot more. But anyway, let's do the H and 0.4, and let's put this at 0.4. Okay, so I wonder why they have to put a star there, but okay, sure. So there will be a new HK epsilon R, and I think I know what this is talking about. This is actually talking about H and whatever comes after H, which is usually we have a H final entry. H final entry, for example, you have the U and the U final. So I think OpenFoam will expect a U, H and H final, and U final for these relaxation factors. And I think for brevity's sake, they use this notation to say, okay, I want H and H final. Originally the entry was 1, and U final, because there's this dot star here. This dot star, it's like it can be used to represent any string of letters that comes after the word U. So I assume it's used to represent U final. So I guess we can leave the the U and U final relaxation factor at 0.4 should not do too much harm. Okay, so no harm done. Okay, the rest we can kind of leave it alone. And we try and check our syntax to see whether anything was missing. So this is the pimple algorithm, residual control brackets, U, P, and H. So watch the highlights. So this is a pimple algorithm. So I have this open and close bracket here, this open and close bracket here, this open and close bracket here, and so on and so forth. Remember, always have semicolons after your entries. And likewise for relaxation factors, because this is a C++ syntax. So that's why we are doing all these semicolons and everything. Okay. Alright. Looks like for oil, it looks pretty well set up. We have FV schemes and fvSolutions at least having some sort of entry. Okay. So that's one part of it. The other part, of course, we want to take a look at the solid. And hopefully after doing this, we can start running our simulation. But I'll stop for now. Since it's 20 minutes, I don't want to drag videos too long. I have a bad habit of doing so. But yeah, thanks for watching. I'll see you guys next time.